world famous. Okay, let's start this afternoon's session then. We close down that. We'll go back to where we were. Okay, this morning I talked to you about the manufacturers of chips and processors and things like that. I attempted to show you a demonstration of the Jetson Nano, which unfortunately went wrong, as these things always do when you have to, unless you've prepared everything in advance. We're going to talk to you now about cameras this afternoon, because processors without cameras don't work. If you know about the processors and the cameras that fit into them, then you can come up with some very attractive solutions which will make you a lot of money. These things that I'm talking to you about, there are companies searching high and low around the earth looking for people who know how to make these things work, which is why we're telling you. If you sit a bit further that way, then you can see the screen. Okay, so we'll talk to you about cameras, we'll talk to you about mobile robots, we will see how we find out who wants to buy some of these things, and then I will talk to you about upcoming workshops, other workshops for people after Ramadan, and then we will look at, we'll mention Chevening scholarships again, in case people want to go and do a British government funded master's degree in England. You can tell your friends, you can try and do it yourself, up to you. So, anyway, the cameras. This is a video by Econ, who are an Indian company who make a vast range of cameras. And this is a camera which is designed for the Jetson.
Welcome to Econ Systems booth at the GDC show at Silicon Valley, San Jose. And we are super excited to launch the camera for the Jetson Nano platform. And as you know, yesterday NVIDIA launched the Jetson Nano to revolutionize the artificial intelligence applications at the edge. And when you're having AI applications on edge, there is nothing that we can do without cameras. And cameras are used for the object recognition, object classification, and variety of applications for the smart imaging and smart vision applications. And realizing the need for the cameras, Econ is super excited to launch our camera for the Jetson Nano, which is a 3 megapixel camera targeted for the applications on the AI applitions on the edge. And this is the camera running on the Jetson Nano development kit. As you can see, we have the 3 megapixel camera connected to the Jetson Nano development kit and capturing the video at 1080p 60 frames per second and displaying it on the screen. And the customers can use this camera along with the Jetson Nano to develop applications, the AI applications running on the edge. We look forward to see you develop innovative applications using our cameras on the Jetson Nano platform. Thank you.
So that was one of the Econ range. Econ are an Indian company which have put an awful lot of effort into developing cameras. However, their order fulfillment and logistics process is absolutely appalling. And they do really silly things like not telling you about shipping charges when you buy something from them, which means you find yourself having a row with the customs or the shippers or people like that for duty and things like that. So one of the things that I need to do is to straighten out the supply process into Morocco for these items. That can go. Okay, we will come to you later. Okay. Right. So back to the presentation. This is a video which shows what they think they will people will use their cameras for. What's really interesting about it is that they have suddenly realized that a camera is not just a camera on its own, and they've put a microphone with it, so that you can not only look at something, you can also monitor the speech, which has got important applications, as you'll see. And you'll find that Intel have gone down the same route of putting something else inside the camera. So it's a camera with added value. Now these are all ideas. It's a USB camera, so it just plugs into the side of your Jetson Nano or your TX2.
Yeah, sure. So that's what we are planning today. So for tomorrow, probably we can go for some sightseeing places. Could you suggest us some places? So for 2 days, we are going to plan for some sightseeing.
Yeah, day one we can actually go to these. That's a huge stretch, and we can cover lots of places over there. That's this beach.
As discussed for the CBC content, we have already prepared this data. Each student in the school will be getting a unique.
So you can mount it on the bicycle. Badge. So they have a whole lot of applications. They have a whole lot of applications that they want you to use it for. Now, they suddenly realized that I might be talking about a lot of cameras coming into Morocco. So suddenly they're talking the magic word. What's the magic word? Begins with F. Samples. Development samples. Evaluation samples. We'll see what happens. Go away. Whatever it is, you're going away. Right. So that's the introduction to Ecom's cameras. Now this is an important thing to learn about. This is the Mythic, yeah?
Also in the first video that they are using 3.2 megapixel camera.
Yeah.
This is the performance of the camera affect the quality of face recognition or object recognition?
Depends how accurate you need it to be, but the number of pixels defines how fine and how accurate the image is. So you don't get some of the strange effects you get with a lower resolution. Okay, so this is the standard interface for cameras. which can go from 1080 pixels all the way up to 8K pixels, which is quite an enormous amount. Now the problem when you have got all that amount of data being generated is how you ship it around the city, the factory, and where you process it. Because if you have got vast amounts of data being generated by one camera, when you suddenly put 100,000 cameras in a city, you have far too much to manage. This is where intelligent cameras come in, because we can do things called scene segmentation, which allow us to pick out the content of an image and then send that as a message, and then use speech processing and text processing techniques to get a summary of what is happening in the city, rather than have people having to look at a bank of 100,000 monitors to figure out what's going on. Now that is an interesting research project which we can do on the Potemkin Smart City. Okay, questions? No? Yes? Okay, camera feeds. A new version of the MIPI standard. All you need to know is basically how to specify the appropriate interface for connecting your camera to a processor. And then Ecom, on their website, provide a very detailed selection chart, which choose applications, resolution, and you can pick out which camera is the most appropriate for your application. Oh, Domoney, bye-bye. Oh well. So I will talk to Econ during Ramadan to see what we can do about getting some example cameras, so we can look at setting up evaluation trials for them and see what we can do from there. The companies which make cameras which are compatible with NVIDIA are listed on the NVIDIA website, and you'll find it's the embedded Mindy ecosystem. If you just Google NVIDIA cameras, it'll give you a list of the manufacturers. Ecom Systems are mentioned here, and Leopard Imaging make some specialized cameras which and lenses which are very, very valuable. Now Intel, remember the catch-up kid? The problem with automated trucks in a warehouse is they get lost. Because all these shelves and racks, they all look alike. You know, when you're in a library and you have shelves and shelves and shelves and shelves, and you go down one of the alleys and you don't know where you are. Well, the same problem happens to little trucks in warehouses. So what Intel have done is they have launched a camera which has got simultaneous localization and mapping built in. So not only can it keep track of where it's been and where it's gone from inertial navigation, so it doesn't have to make use of Wi-Fi, which might not work in the warehouse. It also it has a visual and inertial sensor fused in it, dual fisheye cameras, and inertial measurement. So it will know where it is, and it uses the same Movidius processor as we showed you on the processing stick this morning. This gives the warehouse robot a very great deal of flexibility. So I haven't heard of anybody building a robot demonstrator here, a warehouse demonstrator here, but because warehouses are so important to logistics, we can build a model warehouse here. And we can put in material handling and things like that. You've seen the video of the Ocado warehouse in Andover in England, have you? No? Oh, this is really important warehouse. Let me see. This is what autonomous vehicles are about. These vehicles are picking up groceries from these holes in the floor, from these racks in the floor, loading them onto the truck and taking them on to load up trucks to send out to the customers. The thing about this factory, when we go back inside, the thing about the factory is they forgot to put in any fire breaks. You know fire breaks? Firewalls? So when one of these got stuck in a corner, it caught fire, and because there was no fire break to stop the fire spreading, it burnt the building down. So, being able to program robots to efficiently go and find the groceries in a warehouse, load them on trucks and send them off to where they're wanted is an essential skill. And it's all about making Ducky Bus and Jet Bots work, because you can tell from the little antennas on the back of the trucks that it's got a TX2 in it, because the antennas are a dead giveaway. So that's one of the reasons why we learn about autonomous vehicles, and we can give there's various different ways of doing command and control and tasking for these robots, and you can build in systems which allow them to compensate for failed robots and robots which get lost. Now, people will pay you a fortune to design these systems. Has anybody seen this before? I've met the guy who designed it. I forgot the firewall. Okay. Okay, so that's why they have introduced a SLAM camera for warehouses. Now, if you want to learn about professional robotics, this is the professor of mechanical engineering at Northwestern University, who is also the chairman of all sorts of chapters of the IEEE and engineering institutions in the United States. but he knows about, he teaches all these things, and his courses are online and they're free. Anybody from Morocco who wants to do any courses on Coursera just says I'm in Morocco, and you get the courses free. People like me, I have to pay. All you have to do is say you're a student in Morocco, therefore you're suffering from financial hardship. So they say, well, you can have access to the course for free. He has one of the best robotics courses I know. Here is the book. It costs about £50 if you want to buy it from Amazon, but he knows that people like me can't afford £50 for his textbook, so he also makes it available in PDF format so you can download it and print it yourself. Okay? So, there's a mechanical engineer here? Yeah? Yeah? Okay. Well, chapter 13 of his book is all about the mechanics, mechanical engineering and the kinematics and motion planning of wheeled robots. Now, wheeled robots can be simple things that just move around, or they can be simple things with an arm on them, and things like that. These are all simple things to learn, very straightforward, and we can run a week's course which will capture, or it'll probably be 2 weeks course, which will capture everything that he has in his book, so that you will know the basics of what he's trying to teach. And we can do that as a boot camp, which is an appalling experience if you've ever done one. Okay? So, this is Duckytown and Ducky Bus. I mentioned them earlier. Duckytown is a project which started in MIT to teach students the basis of self-driving technology. They span it out into University of Montreal and ETH Zurich, and I'm in the process of introducing Duckytown into North Africa. Hassan Berbia was telling me that he would like to set up a chapter of Duckytown here in Rabat, and I would be very happy to help with that, and we'll see if we can bring it to Marrakesh and Kenitra as well. So if you're interested, you or any of your friends are interested in learning about all the technology of self-driving vehicles, lane following, vehicle control, collision avoidance, route finding, location, and things like that. You're very welcome to join in, and we want to enter a team for a number of teams for the International Driving Olympics, Artificial Intelligence Driving Olympics, which we talk about here, no, not there. We talk about in a later slide. So if people are interested in that, we'll tell you more. And then this is JetBot. Did I pass around the chassis of JetBot? Yeah, I did. Okay, so you've seen it's 3D printed. It's very light. The parts are very simple and straightforward. Takes about half a day to assemble it. Runs on a pretty large battery, and it has a simple camera on the front, and you can control it by Wi-Fi from a PC with a Jupyter notebook on it. So you can learn all the basics of driving your robot from your PC, and then you can let it loose in a real city. Because we're not using, if we go back to the previous slide, where I have Ducky Bus, this has got road signs. It's got road signs which identify that there are crossroads and things like that, which are QI coded. So we can experiment with advanced location identification, because if we build a real town, or a model of a real town, we can have the vehicle recognize where it is from the buildings, the distance away from the buildings, and other items, and they will recognize real road signs and things like that. Now, if you can put that on your CV when you go along for an interview, people will fall over themselves to give you a job. And as I told the guys in Marrakesh, Ford are paying $200,000 a year for people who know about these subjects in their first couple of years. Unfortunately, you have to pay tax on that. No, nobody laughed. Okay, so that's Ducky Town and Ducky Bus. JetBot, you find the instructions for building printing the 3D robot online. You find a parts list, which is all the bloody American parts, but I'm assembling a parts list in England for parts that we can obtain in Europe, and we will see what we can do about making them available to you if you want to buy more Ducky Bots. Now, I want to build this is Potemkin Smart City. What it is we have a model city, and we photograph the buildings in the model city, or the city that we want to model, and then we can laser cut from the photograph the outline of buildings. So we can build a real city for the vehicles to navigate around. We can paint the buildings. We can also generate, instead of using this vanilla 3D shell, we can generate shells of real cars which take the place of this. Same three-wheel motion, so you control it with the same program as JetBot, but it looks like a real car moving along. So we can generate real traffic jams, we can generate real traffic accidents, and we can generate complete snarl-ups like that. Now that has got the advantage. Now, if I can, I've got to figure out how to make that larger. What comes out of this is we can position fixed cameras around it, which will analyze that scene. Okay, and enough cameras around it will be able to analyze that it's gridlock caused by this car and those buses and things like that, and we'll be able to give instructions to the vehicles round about, while the higher city management organisation can stop cars joining the traffic jam, and it automatically unscrambles itself. And you can control the traffic lights and things like that. Now, that is a big project, but if people take part in that, they will be very, very employable anywhere in the world. And maybe I'll be coming along to your party when you get that $200,000 job. Okay? And anybody that thinks I'm telling magic fairy stories about the $200,000 job, I can show you the press release. There are 4 companies in Philadelphia who are desperately competing for graduates who understand these things. Okay, and then in Rabat, we want a large-scale road traffic smart city where we can build replicas of real traffic scenarios, or Jamal Sana. We can mount cameras from Econ or other camera manufacturers in strategic places around this roundabout. There's a complete PhD in figuring out where to put the cameras. How many cameras do you need to put around a roundabout that size with that number of cars going through? Nobody knows yet. So that might be a project the Minister of Education might fund. Am I making sense? Yeah. Nobody's gone to sleep yet. Okay, and then there's Mona. Now, do you remember I said that sorting out this kind of a traffic snarl-up, sorting out this kind of a traffic snarl-up, it's very difficult to do it remotely. You either have to send a policeman down and he will only make it worse, or what you can do is treat these vehicles which are stuck in a traffic jam like swarm robots. And this is a small swarm of vehicles like this one. This is Mona, a swarm robot from University of Manchester. And what it does is it communicates with the robots near to it. It doesn't care about robots far away. It only talks to the ones which are near to it, like shoals of fish and swarms of bees and flocks of birds. They communicate among themselves and will sort out the traffic jam, providing there's nothing else being added to it. So if the city moves the traffic flows away from the traffic jam, then the vehicles which are stuck in the traffic jam can sort it out automatically among themselves without needing overall command and control. You can have a look. You can take the top off. The battery stays in the top, and it's just got 2 simple motors. And there's a very small processor in it as well. Okay, so that's really all I've got to tell you about mobile robots. We can try and restart the nano demonstration from this morning, or if you want to take a short break, or we can go for tea break. Tea break is not planned until 15:50, and it's what, 14:45. Tea break is at an hour. Other questions? You can examine format of the robot vehicle. This is the back wheel, which is an idler wheel, just a simple ball roller. Fits into there. That's supposed to come off, which is good. And then you put the processor on top and two motors in there to drive the two front wheels. So what I'm trying to do is to get people who would be interested in joining us for the Ducky Bus and building the Potemkin Smart City. And there are enormous amounts of possibilities for small companies and little jobs in building the various pieces of it. If we can have a model of a real city, we can take pictures of various traffic scenarios going around roundabouts and through crossroads and things like that, which will tell us what is happening, and then we use image recognition to identify the condition that's going on. If people are interested in that, we can see who would like to join in that kind of project. Okay. If
will not be difficulties in pre-legislation to put cameras in the...
Pardon?
How about legislation to put cameras in
In the model city?
Yeah.
No problem in the model city.
And model city.
Yeah.
In a real place.
Yep. It'll be, and we can print real 3D shells of real cars, so we can have real looking traffic jams and traffic accidents, things like that. There are so many PhDs that come out of this project. It would be difficult not to find people who would take part. So, what do we want to do? We have an hour before tea break. We can see if people want to take the tea break early, or we could do the stuff. Hmm? Hmm? Yeah. Yeah, with 1 hour now. Why don't I bring the next set of presentations for cooperation opportunities, bring that forward, and then we can finish after the coffee break.
After the coffee break, or we can do all now?
Do it all now?
Yeah.
Okay, in that way people can go home early and get some sleep. Okay? Yes?
Considering program used in Mona, is it available on the internet? Or?
Yeah, it's basically an Arduino, comes from an Arduino development system. But we can put you in touch with the researchers at the University of Manchester.
This would be good.
Yeah?
Yeah.
What I'll do is I'll show you a Swarm Robotics video. That's what we'll do for the next you can be reached. takes about 20 minutes to run, and it is really, really good.
When we look around us in the natural world, there's these amazing examples of collective intelligence that seem to arise from very, very simple individuals that are working together. And starting with the example that he said, ant colonies are just this amazing example, very annoying example sometimes, but they search through these huge territories for food, making these trails that are like super highways to get to the different food sources that they want. And if the food source is too big, they can actually even work together to move it around, whatever that thing is. And if they're annoying people, we can get around what the annoying people do to them too. And it's not just ants. Bee colonies do this as well. They do it in the air instead of the ground. And one of the other examples that I find particularly exciting is the way groups of insects can build. So these huge termite mounds, they're 10 meters high in Australia and Namibia, are built by just centimeter scale insects that are working together, moving little pieces of mud, and creating this system that is huge and self-repairing, which is really an amazing example. You think of bird flocks or fish schools, I'm sure this is something many of you here might have witnessed firsthand, is how they seem to move. You come close to them and it's like they turn on a dime. So who's in charge? Who's in charge in any of these systems? It's so fascinating to watch this collective behavior come together. For me, I think there are 3 reasons why I find these systems really striking. So one of the first reasons is that when you look at an individual, it seems so tiny, so small compared to the sheer size of the swarm. And it seems mind-boggling that this group can coordinate at all when one individual that's at one end can't understand what's going on with another individual at the other end. So how is it that they coordinate? And they do coordinate really well, and the other sort of striking feature is it seems that they coordinate without leaders. So there's no single fish that is telling the swarm to turn or telling the school which way to go. There's no ant that says this is where the trail should be and these are the food sources we should exploit. Somehow, instead, there's a more self-organized process that these systems emerge from lots of individuals, somewhat democratically, running these really simple rules. And from these simple rules comes an intelligence that really only emerges at the group level. And this, I think, is just a really powerful idea that individuals could be limited, could have limited knowledge, and yet, by getting together in numbers, we would have this power in numbers. So, what if we could build our own artificial collectives this way? What if we could build systems where we didn't have to build the perfect individual? We could build an agent that was simple and just make lots of them, and somehow, together, without any supreme leader, these agents would be able to do things we want. Not just do things that already exist in nature, but do something new for us. So for example, coming back to my termites, what if we could build robots that could build structures much larger than themselves and could do it just like the termites build these mounds and nests, except they would build you what you want. I'm not sure if you want the Eiffel Tower, but it seemed appropriate. So what would it take to create these kind of artificial collectives? So when we started this project, we were faced with 2 different problems. One is creating even just one individual that is close to what a termite is capable of doing. So making one robot that can build and move around. And it actually turns out just that is still a grand challenge for AI. We're really struggling to even arrive at the intelligence that an animal has. So we'll make our robots and they'll be somewhat limited. And then the second challenge is, once we have this limited robot, how does it cooperate with others so that it can achieve an intelligence, achieve a property that is so much more than what that individual robot can do? How can I have hundreds of robots collaborate? So the interesting thing is that, of course, when we're thinking about simple rules for robots, it's not actually the case that somebody understands what the simple rules are that operate in termites. We don't actually know that. What we do know is that termites seem to actually cooperate without talking, which is an unusual feature. So instead of termites meeting each other and discussing what they're going to build, they can actually react to things in their environment. So they might see a building pattern and react to that and decide what to build. And the interesting thing is that once they build, they influence what others will do instead. So now you're communicating using the repair them when the environment changes by simply looking at building patterns. So we started this project to build robots that could cooperate in the same kind of way. And our first challenge, as I said, was making a single robot. So our single robot has to do one important thing, which is move. So it needs to move over different terrains, and it needs to be able to climb over the things it builds. So we built a robot that climbs over stairs, and it builds stairs. And by building stairs and climbing over those stairs and building bigger stairs, it can build its own structures. So it climbs, and it picks up material with its claw, as you can see here. Now you'll see it pick up a piece and place it down, and we start to create this single robot that can do all the actions that are necessary. And one of the things you'll notice is that as it's placing this block, this robot actually has trouble doing it. So it's slightly slipping, it's moving, it's turning, and this is where the intelligence comes in. So how does it sense what it's doing and sense of the world? So our robot has lots of different sensors. It has pattern sensors, so it can see the patterns on the block. That's how it sort of navigates through its world, knowing where it is. It has distance sensors, so it can feel if there are obstacles in its way. It has a tilt sensor, so it has a sense of balance. It has a touch sensor, so that it knows when it's picked up or let go of a block correctly. And when you put all of this intelligence together, we get a robot that sort of is beginning to approach the autonomy that we think any ant actually already has. It can climb up the structure that was built by someone else, it can carry things in it, it can place it, and it can climb over the things it built. So the next step is, what are the rules? How do you get a bunch of these robots to actually cooperate? And one of the things we discovered was that we can actually design our own rules. So if you gave me a picture of a structure that you wanted, there is actually a way to systematically come up with rules that all of the robots, if they ran together, would produce the structure. And the interesting thing about these rules is that they can use the same ideas that I was telling you with the termites. So each individual robot comes to the structure, and it actually just looks for building patterns. It's looking for somewhere to build, and it has to find somewhere to build, but it doesn't really know how many other robots there are or where the other ones are. They're just constantly reacting to things built by other individuals in their colony. So this is a simulation, and here is our single robot actually running the program. So this is sped up, it's probably obvious. So the robot walks around the structure, it looks for the landing strip, and it gets on, gets a block, and then goes and looks for a pattern that says, here's a good place to build. So it's sort of looking at things that are already built. Now, suppose the structure gets destroyed. Well, each time the termite actually comes, our termite robot comes, it doesn't actually have a memory of what's been done in the past. It's just looking for local building patterns. So if another termite comes and builds, it can also take advantage of that nice situation and continue to build. And in this way, these rules have a really nice, robust property. They're actually very, very reactive. And both destruction and addition seem to be able to, be dealt with this one robot. So here you see our final system. We have 3 robots, Isis, Nargan, and Kali. And they're working together to build what is supposed to be their own castle. And the interesting thing is, of course, each of them is completely unaware of the other robots in the process. It's really just each robot is its own individual, building it on top of the actions of the other robots. Now, this is still a really simple system, and maybe it might surprise you to think that it took us 4 years from the point where we thought we were going to do this to get here. But if we imagine other kinds of robot bodies, robots moving sandbags, robots moving beams, we can imagine these cooperative groups building things that we really care about in the environment, and building the way we think an animal intelligence should be able to do. I showed you 3 robots, which of course is a far cry from the collectives I was showing you at the beginning. If you thought of the fish or the ants, there's thousands of them working together. And if you go even smaller, like if you think about a cell inside an organism, these are cells with identical DNA that are cooperating to create a complex organism like a starfish. So even a cell is part of the collective. So what if we could create our own collectives of this scale? So what would it be like to, for example, not have 3 robots, but have, say, 1,000 robots? Right? That would be pretty cool. Well, certainly any one robot is actually actually not going to be as sophisticated as the Termes robots that I showed you before. So we have to sort of make them a lot simpler. In fact, I have one right here. So this is a project that was inspired by this idea that if we have 1,000 robots, then we can start to mimic the kind of ideas that we see in nature. We can start to understand better
These
how
are
those robots
1,000 real
operate.
robots.
And maybe we can start to generate our own rules.
I've bought
So here's a
from
single robot, and here's what a single robot can do. A single robot can move, so it can use these vibration motors, kind of like what you have in your cell phone, to move straight left and right. It can talk with its neighbors through a simple wireless system where it talks to just a couple of neighbors. And every robot has its own computer. So now we can program the group of robots with whatever simple rules we want, simple rules that we think, for example, might come from nature. We could start to look at those kinds of rules. So I'll show you an example here. So for example, if you think about fireflies, you can program each robot to flash its light as if it was a firefly and start to pay attention to what its neighbors are doing and change its flashing. And eventually, the whole group can actually synchronize their flashing. Just the way like an audience starts to clap together all of a sudden in a self-organized way, we can actually recreate those programs on our robots. We can think also about pattern formation. So how is it that cells in an embryo form patterns? So here on the left-hand side, this is a whole field of 1,000 robots. And on the left is a single robot that's emitting some information, and the other robots are forming a stripe-like pattern based on how the information is flowing through the system. So depending on how far you are, you might take a different color. We can program collective motion, so motion in small groups. Anyone seen this before? Motion in large groups. And this video I really like to show because, you know, we made these robots. These are not ants, and they're identical, and we gave them identical rules, but they don't
This
behave
is
identical.
pedestrian or vehicle
They
traffic.
really behave with the variation that we
Jamal's
think
not.
of as having natural systems. So one of the things that I said in the beginning that excited me about having 1,000 robots was really trying to create new kinds of collective behavior. What are artificial collective behaviors that have never existed in nature? Ones that you and I get to invent. So can I invent a program so that these robots self-organize into a starfish shape? Well, we can. And actually the interesting thing is that the program that we use to self-organize something like a complex shape is the same program that combines things from before, like synchronization, movement, pattern formation. You put those together, and you can actually make much more complicated programs that combine those different behaviors. So here, each individual robot doesn't actually know where it's going to end up in the shape. There's no leader, there's no overhead camera. Each robot talks to 10 neighboring robots. But as a group, they're actually able to form a pattern that all of them know is the goal, but none of them know which role they're going to play. So this is just showing some close-ups of that, and so you can sort of see what the size of the robot is in my hand, or maybe not, or maybe afterwards you guys will see some. And, you know, it begins to sort of look like these pattern formation and individuals moving around together. And maybe in the future we'll be able to shrink the size of these robots so that we would think of these really as programmable materials that just sort of, like a 3D printer, you could take a box of this and they'd morph into whatever shape you want. Or maybe they could be larger ones, robots that could self-organize into bridges or self-organize into beams if need be. You know, there's a huge amount of science fiction around trying to think about what kinds of things we could do. But one of the things that makes me most excited to watch this video is that you sort of forget that there is a bot altogether. It starts to look like just one entity. It starts to really look like a collective. And I think that that's getting us closer to that idea that we can create the kind of artificial systems that fascinate us in nature. What will future collectives look like? Well, this is up to, you know, invention. I don't know, and there are many challenges that we have to solve. But there's so many environments where we could think about robotics, or think about the role of robotics, think about the role of artificial collectives, whether it's monitoring our ocean environment or growing our food, or in the future, you know, when we have all these electric vehicles with self-driving capabilities, we're going to have highways full of robots. So how are these robots going to be programmed? What do we understand about collective behaviors? This becomes very important. And I think that, you know, many of this today is science fiction, but the internet is an amazing collective of very small computers, if you think about it. And that was once science fiction. So where is this going to lead us next, I think, is anybody's guess. So what can thousands of individuals do together? The last thing I'd like to say is, of course, there are many things that we can do together, but science is one of them. And sometimes these talks give the impression, I think, that the person who stands here is the person who invented it. But that's not at all how it works. My own talents are pretty limited, and I think that many of you might feel as I do that, if it just relied on the knowledge I have, I didn't even know I wanted to do robotics. I didn't realize that until I was past 30. So what happens when you don't have all of the talent or all of the knowledge required, or even all of the courage that it takes to try something wild and crazy? Well, you look to your own collective. And I have had an amazing experience to work with incredibly talented people who bring their talents as well as their limitations to the table. And as a collective, we're able to transcend completely what any one of us can do. And I think that most important scientific discoveries are that way. Now, are there simple rules that make us work better together as collectives? That I don't have an answer for you. And I have to admit, we experiment with new rules every so often in my group to try and figure this out. But I do think that solving any new scientific discoveries, solving climate change, building the next energy solution, all the things that you hear at this TED Talk, those are things that are not solved by individual talent. It's collective talent. My talent, your talent, and all of our collectives. So I hope you find the collective that best fits your talent, and think about bringing to your community all of the interesting things that I'm sure you all are thinking of. All right, thank you.
Was that interesting? Yeah? Self-driving car that works with the cars around it to sort out a traffic jam. That's patentable. That's umpteen research projects, and there are jobs for life if you learn how to do it. So was that worthwhile? And if you do a good PhD here, you might end up working in that big research group in Harvard. Why not? Remember what I told you this morning? Yes, we can. So, right. Well, it must be nearly time for coffee. Yeah, it's 15:10. What time's coffee? 15:50. 15:30. Oh, that's 20 minutes. 20 minutes until coffee, so we could have an early coffee break, and then when we come back, we'll see if people want to join Ducky Town, want to join the Nano program, want to join the Jet Drop program, or want to join our team putting together a proposal for Champion Smart City. Okay? Ça va? Okay. Pause café jusqu'à 4 heures. So, 4 heures moins 15, 4 back here 4. Okay. Did I show everybody the camera for the Jetson? No? In this box, you've seen this before, haven't you? Yeah. In this box, you have a camera unit which fits into the Jetson, and then the idea being, if we want to put together a swarm of 100 robots, that we get 10 universities to buy 10 each. Okay? And that way we have 100 robots, and then then you have a lens on it, and that fits onto the TX2 that I showed you this morning. Okay. That's what the guys in India have been building. Okay, that's the camera. So we can have lots of little cameras, intelligent cameras like that, which can be reprogrammed. Sell them all through Africa. There are 47 traffic lights in Lagos.